Okay, today we are looking at an interesting Euclidean geometry problem. It looks quite simple, but involves actually a couple of very important theorems in this field. And we are going to watch this animation first, and I will explain how this invariance is derived. So if you look at the original animation on Twitter, so you have a triangle and you put a midpoint on the base and choose an arbitrary point on the base as well. And you connect like this point, vertex to a chosen point, and draw two other Cevians that all three segments are concurrent at a point. So regardless how you move this point, you will have these 4 points on the same circle. So it's concyclic quadrilateral formed by these 4 points. But we can do a little bit more to show one more important thing in this graph, which is not shown here. So if we just draw this thing in Geogebra, and fix A and B, and of course D is fixed because AB fixed, and of course its midpoint is fixed. Okay, instead of moving E around, let's first fix E as well. So we can move around the vertex of C, and then we draw CE and GF H are the points can be arbitrarily chosen. If I just move some point on AC, I can just draw a Cevian, and then once I have C and BH, I can just draw AF immediately. So that's how it works. And then if I move C around, you can see not only I have this circle that pass through 4 points, but also you will see that the line HFJ are and the intersections with AB are fixed on the x-axis. So this is actually the key point to prove this thing. So let's start. So to eventually work out this problem, we need some theorems to use at hand to show some very important relations inside this diagram. The first thing we are going to mention is this configuration, the whole configuration. This thing is called a projective harmonic conjugate. So this is basically a very typical structure we need to use. And once we have that, we can see that if we match the diagram with ours, you will see LMKN is just CHGF here, okay? And the A is the intersection of the extended line LM and NK, so it's here. And B is the extended intersection on extension of MK and LN. So this is B, okay? And E is the D here. So it's sort of like a diagonal line of this quadrilateral. So LKD is in the same line, same thing as CGE in my case, okay? And D is fixed midpoint, which is not shown here. So once you have this diagram, a very important relationship is called harmonic conjugation. So it determines the relationship between AB point and the CD point. And once we have AB fixed, in my case, and fixed D or C, we can immediately compute C or D. So for example, we have AB fixed and move D around, then C is uniquely determined in this case. And this is something called cross ratio. And to prove the cross ratio, we need another interesting theorem in geometry. It's called Menelaus theorem. You can find that on MathWorld. So it gives you a very strong relationship between the segments in this diagram. So if I have a reference triangle ABC, it's intercepted by line DEF, and E is on BC, F is on AC. And then I have AD times BE times CF equal to BD times CE times AF. These are all undirected length. So we sometimes in the Euclidean geometry, you will have AD is like positive distance and DA is the negative distance. So in this one, if we purely think about the scalar relationship, this is something we have. And this relationship can be quickly proved for the Euclidean relation in the Euclidean case. Okay, now we have this configuration. So we are here to quickly how you prove this relationship. And usually we write it as a equation between two ratios. It's like AD over BD times C over BC and times CF over AF equal to 1. So that's more commonly viewed equations. So let's also can look at the demo. So you, regardless of how you move the vertical C and choose different location of F on AC, the ratio are the same, or the products remains the same. Okay, so let's take a look at it, the proof. So if we have the ABC reference and the EDF, that's the interception, the only thing we need to add here is a segment BP. BP is chosen that AC is, P is on AC, and BP is parallel to EDF. Okay, that's the line. And we use some very obvious relationship in the similar triangles. So let's see, we have AF over FV. Which is the same thing as AE over EP. Okay. And the second one we have is BD and DC. And this is CE over EP. And lastly, we have CP over, or CE over EA. And this thing remains itself. Okay. And now let's try to make productions on all the left-hand side and the right-hand side. We have AF over FB times BD over DC times CE over EA. So basically this is the path. This way, this way, this way. And this way, and then this way. Okay. And replace all the expression with RHS. AE over EP times CE BD. Yep, that's the reverse. PE over EC. Times PE over EC. And times CE over EA equal to 1, because we can see that these two things cancel, these two things cancel, and these two things cancel. Okay, so eventually you will have this relationship. And let's go back to our diagram. Okay. So in this diagram, we obviously will have it's AK over KB AK AK over KB times BF over FC and times CH over HA equal to 1. That's in triangle ABC intersected by HFK. But we also have another relationship is A All right. So then the other part is from the Cevian, 3 Cevian being concurrent in triangle ABC. You have and this is E, A, B, and this F, H, C. And in this case, we use a sister theorem of a Menelaus theorem. It's called the Ceva theorem. So it always looks just like the Menelaus theorem. You have the product of length equal to the product of other set of length. So in this case, you have BD times CE times AF. So it's an easier way to remember that, to memorize that is BD divide DC times CE divide EA and times AF divide FB. So you have a sort of a cyclic path that give you a product of ratios equal to 1 exactly. So in our case, it is AE is AE EB BF over FC times CH over HA equal to 1. And you notice that these two parts are the same. So therefore, we have AK over KB equal to AE over EB. And this is exactly what we need for cross ratios. Okay. So you have, for example, 4 points on the segment. And what we have is AC over CB equal to AD over DB. So you basically just switch AD and BC here. So you have AC over CB is equal to AD over DB. Okay, so it's kind of strange to find this relation at first hand, but actually this relation is very easy to remember if you just make it algebraic, which I mean just by not too much focus on the geometric part, but only on the algebraic relationship you have. So this, because the ratio here, given that if we fix A and B, you choose somewhere C along the AB, you can immediately determine the D. Okay, so let me just solve this thing quickly with easy one variable equations. So because the relation we have here is, let's just switch back to this diagram, is A D over DB equal to AC over BC. So assume length of AB is equal to 1 because we have the ratios here. So it really does not matter what's the absolute value of the length of AB, but we can just choose a relative ratio to be a fixed number. So to simplify the computation, I can just randomly choose the length of AB to be any other number. So 1 is probably the easiest one to do that. And the C is somewhere between A, B. So C, I can choose the distance between C and B to be x. And then the distance AC is just 1 minus x. So the cross ratio just simply says if BD is a given number like lambda, it's a known lambda. So I can solve for this x in terms of the length of AB and the length of BD. So if AB is 1 and BD is lambda, so you just plug in this relationship into this equation, and this is what we have. And eventually we have x is equal to lambda over 1 plus 2 lambda. Okay, and then you can easily quickly verify that we have a KD times KE is a constant. So here, because in this case, E is fixed, so BE is fixed, which means the x is fixed. Because the x and the lambda are basically interchangeable. It's a 1-to-1 relationship. So fix x, you fix lambda, and fix lambda means you fix x. So that's why, regardless how I move this thing, the k is always the same if I fix E. Okay. And then you can just verify that dB times dA is equal to dC times dm. M is the midpoint here. Okay, so this one gives you an algebraic expression of the exact equation you have. Okay, so to have that thing, the conclusion you see in the original Twitter video, we also need to show that these 4 points are actually on the same circle. So here we can see that because K, J, B, A, I actually is a perfect example of power of a circle. Or we can say J, B, K, and K, I, A, the triangles are anti-parallel. So we have kj times ki equal to kb times ka. This is one relation. Okay. The other thing is, because we have shown that A, E, B, K are harmonic points in this one, and we also did a formula this thing equation solving process to find the length. So in this diagram, it's dB times dm. dc times dm equal to dB times dA. So the points, if we switch the point labeling in our case, it is exactly kb times ka equal ke times kd. Which means kj times ki equal to ke times kd. Okay. So kd times ke equal to ki times kj. That's so in this case, triangle kje and triangle KDI are antiparallel. So in this case, IJED are concyclic. And that's the end result of the proof. So this thing called a complete quadrilateral, it has lots of interesting properties. It's way beyond the problem we have discussed here. But many important properties are derived through harmonic conjugations and rotational symmetry. So I have a function that includes lots of great examples for Mathematica users. So if you go there and you can see the harmonic quadrilateral is strongly associated with this type of problem. And you can find some very important properties there. Typically, a circle inversion property that transform the harmonic quadrilateral into a perfect square. So this is a sort of a very advanced theorem and topics in Olympiad level competitions. So if you like it and you probably want to practice more on this type of problem, typically on harmonic conjugates, because it also implies Apollonian circle, which is strongly related to circle inversion and lots of hyperbolic geometry stuff. All right, thank you for listening.